So how can we increase the analog to digital conversion resolution? We have an approach called oversampling and averaging. We take the samples at much higher rate than needed, and then we perform decimation, reducing back the sample rate by averaging of several consecutive samples. That's why we improve resolution. We have a trade-off between conversion speed and resolution. Now, the idea is the following. Here is our signal, its spectrum, and up to a maximal frequency, Fmax. Now, if the Nyquist frequency is here, the half of the sampling rate, this is our quantization noise. The area is its power of the quantization noise. This noise, we consider it as not non-correlated. It has a flat spectrum. So when we increase the sampling rate, the quantization noise power stays the same. It doesn't change. But it is spread from 0 up to the Nyquist frequency. Obviously, when we increase the Nyquist frequency, this rectangle has the same area as this. But in our band in interest, the noise floor obviously decreases. So, what is we have increasing the sampling rate and low pass filtering. Low pass filtering is can be done just by averaging. This is the idea shown in frequency domain. How can increase the sampling rate? Our formula is 602 by the number of bits plus 1.76. This is our base formula, but now we have an additional improvement. When we double the sampling rate, we get a half a bit of resolution more effectively. If we increase the sampling rate by a factor of 4, we get an additional bit. 3 decibels in power is 1/2. So if we increase 4 times the sampling frequency, we will get an additional 6 decibels, which is equivalent to 1 bit more. Here is the idea. We have n-bit analog to digital conversion. It works with sampling rate much higher than necessary, and after that we have low pass filtering and downsampling, decreasing the sampling rate back to our requirements. So we have here high speed and low resolution. Now, after that, we have low speed with higher resolution. Just averaging is not the best low pass filter as we can see, but it still works. This approach is not always valid. We have two types of noise. The first type is the quantization or granular noise, and the second is the white noise. If the quantization noise dominates, this approach usually fails, because for low resolution analog to digital converters, the quantization noise is the dominating one. So if we try to average, the result is not good. We don't gain more bits, but we have somehow a contra-intuitive approach to overcome this problem. Actually, this technique is called dithering. We inject an additional noise, which is wideband as white noise, and then we perform our averaging. This prevents the ADC value to stick on a given level and to stay in this level. Just we inject in such noise, we have fluctuations about around the quantization level, and when we perform averaging, the results are very good. This noise should be with standard deviation of about the least significant bit. Maybe 1/2 of least significant bit, or 3/2. Actually, we increase the noise floor, but this noise that we have injected is with flat spectrum, and our averaging works well. For some analog to digital converters which are with high resolution, this approach is not needed, because they have such noise. The dominating noise for high resolution analog to digital converters is not the quantization noise, but the white noise. It dominates. So the averaging is very appropriate in such a situation. You have, for example, 24-bit analog to digital converter. But the resolution, the effective resolution is, let's say, about 18. From 18 to 24, we have 6 bits which are corrupted by noise, white noise, thermal noise. When we perform such average, we can increase the effective number of bits, let's say, by 1 or 2 more.
What about working in different frequency bands? How does this play a role into the noise component? Does it remain the same regardless of which
yes.
frequency band?
As you can see, if we model the quantization noise as flat, it doesn't matter the frequency. Actually, we model this noise as flat. Actually, it is somehow correlated noise, and the spectrum is not very flat. Its autocorrelation function is not very tight, and the spectrum sometimes is concentrated here, but we are going to discuss on another approach when we are going to discuss sigma delta techniques. Now, in short of analog to digital converter parameters, here is given the transfer function of the ADC. Here is the analog input. Here are our digital codes. For simplicity, there are very few. Ideal function is a straight line, but in practice, it is a staircase here. The ideal is a straight line. The real is a staircase because we have limited quantization levels. For our best analog to digital converter, the quantization error ramps from half least significant bit minus to the plus least significant bit. It stays in the range of least significant bit error. We have two types of errors, static or DC errors, and dynamic, we call them noise error. We will start with static ones. The first one is very obvious. This is offset error. Offset error, we have here with dash line the ideal ADC transfer function, and here with solid line we have an example of analog to digital converter with offset. Here in this example, the offset error is 1 1/4 LSB, measured from here to the mid step. This error is can be easily compensated. It is present in the as same is in all steps. The next type of non-ideality is the gain error. The gain error is measured at the endpoint. We have nominal gain point and the actual gain point, and we have in this example the gain error here. Gain error, if our ideal is something like this, with gain error we have a different slope. Here is the gain error. Offset and gain. This type of error is also very easy to be removed. Next, differential non-linearity. Differential non-linearity is measured as the deviation of the ideal line for each step. Here we have a possibility, if we have differential non-linearity that exceeds one least significant bit, we have a possibility for our analog to digital converter to become non-monotonic, and a possibility to have missing codes. Missing codes are those that we expect to see at the output of analog to digital converter of some input voltage, but it never appears at the output. Example of missing codes, maybe now we have missing codes. The second one is the integral nonlinearity. The name suggests that this error is measured as summing or integrating the differential non-linearity. Up to this point, let's say, we accumulate every differential non-linearity and we get the integral non-linearity. Usually, the manufacturers specify such error as its maximum.
Would that be the area of this?
No, the area. You have differential non-linearity here. You have another differential non-linearity here. When you sum this and this, you will get the integral non-linearity at the second point. When you add the next non-linearity, you will get the integral non-linearity in the third point, and so on.
How do we get it for 1 point?
The 1 point is only for the first point.
Let's see.
The integral non-linearity is the same as differential non-linearity in such case.
Yeah, but how would you get it calculated, or like I'm trying to think of, like, is it the variance in step size or
Deviation of the step size.
deviation of the step?
Yes.
And it's different for each one because the step is different for the rest?
No, the error is different for every step. You have differential non-linearity in some value for this step, differential non-linearity some value for this step. They are independent of each other. When you sum them, you get the integral.
But I'm trying to grasp like what is causing this.
Non-linearity. Non-linearity is in manufacturing technologies.
Okay. So basically, this is how this much deviates from a straight line.
Yes. They manufacture some kind of analog to digital converter.
And it's different for the different frequency range, so that's why it would be different for the different.
No, we don't talk about any frequency. We talk about for DC. You apply a DC voltage.
Okay.
You apply, for example, 2.5 volts.
Yeah.
But
okay,
you have a deviation, and they determine it by experimentally. They took a lot of samples of such chips and make statistics. And the last error is the absolute accuracy. It includes all mentioned up to here. The maximum error. Integral nonlinearity, offset, gain error, and so on.
The nature of all of these is actually instrumental.
Yes, always.
Okay, that makes sense.
Mm-hmm.
Because previously we were talking about quantization, which is not
We have talked about an ideal case of quantization.
Yeah.
The quantization depends only by the ADC resolution. But here we are going to manufacturing deviation from the straight line. Noise parameters. We are familiar with this. But now we can consider the allowable effector number of bits.
Yeah, that's it.
We have here the worst case when we add the one bit, the least significant bit non-linearity error, which is acceptable, and our SQNR in this case is a little bit lower than there is something wrong with this formula. this here the sign should be minus. My mistake. Total harmonic distortion. This is the root mean squared of all harmonics divided by the first harmonic. Here we talk about not DC, but with AC signal. And the signal to noise distortion, it combines signal to noise ratio and total harmonic distortion. There is some misunderstanding here. Some authors consider signal to noise ratio as signal to quantization noise ratio, but they are almost the same for low resolution analog to digital converters. For high resolution analog to digital converters, the white noise dominates over the quantization noise, and we have a difference here. This is just signal to noise ratio, and the effector number of bits. Those bits that are free of noise, in simple words. And now we are going to make a review of some common analog to digital converters architectures. The first one is the simplest analog to digital converter, which is 1-bit analog to digital converter. We have such thing. This is a comparator. It takes the difference here and outputs one of two levels at the output. We can consider this as 1-bit analog to digital converter. It can be found in any analog to digital converter in the architecture. Usually we make positive feedback, not given here, to make hysteresis, because when the two inputs of this op-amp are very close to each other, we have oscillations of the output of the comparator. So to prevent this, we involve hysteresis. This is operational amplifier with a very high gain, without feedback. The first architecture is so-called flush analog to digital converter. We have a voltage divider with resistors and many comparators. The idea is this output behaves like a bar graph. For a given level of the input voltage, this may be 1, this may be 1, this may be, up to here. If you want to achieve, if you want to make, let's say, 8-bit analog to digital converter, you should have 256 number of such comparators. It's not very convenient for manufacturing, a lot of power consumption, but this is this is the faster analog to digital converter at all. The next type is successive approximation register. Very common analog to digital converters. Their resolution starts from, let's say, 8-bit up to 14. I've never seen such architecture for 16-bit because it is hard to build this digital to analog converter. What is the idea? Are you familiar with the binary search algorithm?
You mean like
Dividing by 2 by
every
2
time? Yeah.
every time. When you have sorted array and you have to find an element. The fastest way is to separate by 2 and by 2 by 2 and so on. The idea here is the same. You starting by writing 1 as the most significant bit here. And this digital code is converted to an analog voltage, and we compare this with the actual input voltage. Our comparator will have at the output 2 states, 0 or 1. 1 if we are below, 0 if we are above this voltage. And we decide which half are in. We start by dividing by 2, and if we are in this range, we can divide another by 2. And if we are here again and again, and for very few steps, we can find the code that is that represents this voltage here. This code can be found in this register. And finally, we can write this code from digital interface. Next architecture, dual slope. We have very precise crystal oscillators, very fast, with very stable frequency. Why it is important? Because we can convert the input voltage to time. If we can convert input voltage to time, we can measure very exactly this time. How? If we have a crystal oscillator, we can measure the clocks, the number of clocks in given time interval. Such number of clocks is equivalent to the input voltage. But how can we convert a voltage to time? The idea is simple. We can integrate the voltage over time. Let's imagine we have a DC voltage. If we integrate the DC voltage, we will get if we have a constant voltage, its integral is a line with slope proportional to this value. We integrate the input voltage for a fixed time t, and this slope is just the input voltage over RC. Situation is the following. We have an amp, and this circuit behaves as ideal integrator. If we apply constant voltage, this output ramps up. But this slope depends not only by the input voltage as we want, but depends on resistor and capacitor. We have a problem because such elements are not exact. value, not exact value, and they have temperature drift, time drift, and we will not achieve correct result. So how can we solve this problem? We integrate this for a fixed time t, and at this point we apply at the analog to digital converter the reference voltage, which is very stable, which is constant. When we apply this, our integrator starts to ramp down. This slope is equal to the reference voltage divided by R by C. We have a constant slope. So if we consider this value, we can make the following equation, and we can express the time Tx, which is the time when this ramp approaches 0. When we express, we can see that we are not dependent on resistor and capacitor anymore. We are only dependent on the input voltage, reference voltage, and the first interval of integration, which is very, very exact. This is the idea of dual slope analog to digital converters. Here is the architecture. This integrator, reference, we switch, we apply the reference voltage at the end of first integration time, and we want to find the integration time, so we have a comparator to detect the end of integration. When we count the clock pulses for such integration time, we have effectively our digital clock. Such analog to digital converters are very slow. They sometimes provide 1 or 2 or something in such region of number of conversion per second. They are intended to be used for slow changing signals, but the resolution is very, very good, very high. An additional benefits: if we have noise in our input, this noise is also integrated. When we integrate the noise floor decreases. We can cancel the noise. Also, we can cancel the interference from power line. We can integrate for a time that is an exact multiple of the mains frequency, mains period, power line period. So we can integrate in a period that is exact multiple of the period. So when we integrate in such period, one more, you can see that we can cancel completely the influence on the power line. The next pipeline, we have a structure which is somehow we have multiple stages of analog to digital converters. Let's talk about the simpler case when we have multiple elementary stages which consist of 1 bit analog to digital converter and 1 bit of digital to analog converter. When we apply the voltage here, the code for the analog to digital converter is fed into the input to the digital to analog converter, and we get the difference. Here we have 1 bit analog to digital converter, so we have a resolution of 1 bit, which is the half of the whole input. So when we take the difference, we can multiply the difference by 2, which is which corresponds to the half range. Now we have another analog to digital converter, and so on. We have many elementary stages for each bit. They are fast analog to digital converters, and they have good resolution. The next thing is delta sigma analog to digital converter. The idea here is similar to the averaging and similar to oversampling and averaging. We have, in fact, one bit analog to digital converter, just a comparator, and 1 bit digital to analog converter and integrator. We have here a stream of bits, and this stream, the number of ones in this stream is proportional to the input voltage. So we have here very high speed, but just 1 bit resolution. We can increase the resolution with digital filter and decimation. Sometimes in this frequency here maybe 100 kilohertz or megahertz, and after digital filtration and decimation, we may have sampling rate very low. For example, several conversions in second. But here the resolution is 1 bit. Here the resolution is much more. For example, 16 or more bits. One interesting thing here is the waveform. Here is the output of the integrator. Here we apply 0 volts input voltage. The number of ones is equal to the number of zeros. When we apply voltage half of the reference voltage, you can see the number of ones is increasing and the waveform of the integrator changes. So if we make an average of such thing, we can increase the resolution. Here is shown a model of the delta sigma analog to digital converter, and the simple analysis show the same, the following. This is the signal term, this is the quantization noise term. Here we have transfer function that is 1 over f plus 1. Here we have a transfer function that is f over f plus 1. Here we have low pass filtering, and here we have high pass filtering. Actually, the quantization noise is high pass filter, and when we apply high pass filtering of the quantization noise, we move it power spectral density from low frequencies into the high frequencies. And this leads to improvement of signal to quantization noise ratio, because if we apply our digital filter, we have a little bit of noise here. The higher the power of noise is moved into the high frequency. And for the digital to analog converters, in short, the same static errors, offset error, shown here, gain error, when we are in the last point, of course, differential nonlinearity and integral nonlinearity, and the total error, as similar as to analog to digital converter. Now, several words for the digital to analog. This is the simplest digital to analog converter, just a switch, reference or zero voltage, 1 bit digital to analog converter. And the next architecture is Kelvin divider. We have a voltage divider, which is switched to the output by one of these switches, which are controlled by the input code. We have a version of the Kelvin divider. We call this digital potentiometer. We have a tab here. And fully decoded digital to analog converter. We have a string of, we have many equal resistors. We can switch some of these switches, not just only one, but we can switch more of them. And we can fit this current into the op-amp. This circuit is the inverting op-amp. It is just a current to voltage converter. We have current increasing or decreasing when we switch some of these switches. Binary weighted digital to analog converter. We have different values of resistors. Half, fourth, and 1/8. This corresponds to the most significant bit. This corresponds to the least significant bit. When we enable a given switch, we can make a voltage that corresponds to the digital code. Here in this example is it is number of levels 2 by 4. Such analog to digital converter is very hard to be produced because of the very different values of the resistors. We can use a so-called air-to-air network. Now it behaves in the same way as this version, but with this network we use only two values of our resistors, R and twice R. Very easy and to be manufactured and trimmed, because we want very close matching values for air and Tourette, but the resolution is still low. And the last one will be sigma delta digital analog converter. It works in the opposite way as the analog to digital converter. In the analog to digital converter, we have high speed of low resolution data, and at the output we have low speed of high resolution data. Now it is the opposite. Here is our digital code. We increase the resolution by, we increase the sampling rate by interpolation. And this digital delta sigma modulator is realized in software, and at the output we have very high speed of 1 bit data. Now, after this 1 bit DAC, we have analog filter that converts this high speed data into analog voltage. Because of the high frequency here, the complexity of our analog filter is usually very, very low. And because we have two topics to cover, the break is 4 o'clock. So, the next topic that I want to talk about is linear time invariant systems. We will discuss types and some properties of systems, time domain characteristics, frequency domain characteristic, Laplace transform and its application in analysis of linear time invariant systems, and the Z transform. Here the system is a meaningful interconnection of components, and the idea of the system approach is to regard the system as a black box, and this system accepts some signal at the input and produces another signal at the output. We are not interested in the internal architecture of the system. We are interested only on the system behavior. We have continuous and discrete time systems. We have memory and memoryless systems. Continuous time systems are those that process continuous signals. Obviously, discrete time systems are those that works with sampled signals. A system takes into input the signal X and produces some output Y. We denote this changing by S. Memory and memoryless systems. Memoryless systems depend on the current value of the input signal, whereas a memory system take into account some previous values of the input signal. The first property is the causality. It is a very simple property. A system is causal when it depends on the current input and of its history. A causal system doesn't depend on the future. Very, very strange. Example of causal system and example of non-causal system. Y depends by some future of the input X. The next important property is the linearity. If we apply a sum of two signals to the system input and multiply them by some coefficients, at the output we have a sum of output signals times the same coefficients. So we have here the principle of superposition. If this principle is satisfied, we have a linear system. In a frequency point of view, a linear system just changes the magnitudes and phases of the frequency components. A nonlinear system generates new frequency components that are not present in the input. The next property is time invariance. The idea is if we apply the signal with some delay, the output will be the same with the same delay. Just at delayed input, we have delayed output, and the system behaves in the same way, independent of time. If we combine this property, time invariance, and linearity, we have linear time invariant system, or LTI. We are going to talk about LTI systems. For such system, the superposition is the key concept here. So now we have our system as a black box. We want to know, we want to review their characteristic. How can we achieve this? We can get such characteristics in time domain, and if we get such description in time domain, we can predict the output when we apply an arbitrary input signal. Such test signals have to be with continuous and non-zero and unlimited spectrum, because if we have sampled spectrum, we may miss some important properties of systems at a particular frequency. Which are our test signals? The first one, we are now familiar. This is our Dirac delta. Why do you think? We think this is a good test signal? Because its spectrum is flat and equal to 1. And the next test signal is unit step function, Heaviside function. These two signals are for continuous time systems. this signal and in signal can reveal all system characteristics if we apply them at the input. Here we have a definition. Excuse me. Here is a mistake. Should be u of t 1 for t greater than 0 and 0 for t less than 0. Here should be t not there. So we expect some relation between such functions, and for discrete time systems we have almost the same. We have Dirac delta in discrete version and step function in discrete version. The main difference is when we have delta of t, the amplitude is infinity, but the area is 1. When we have delta of n, its value is 1. That's the difference. This thing doesn't exist in real world, but this exists. They are related. If we take the first derivative, our step function, delta function, the first derivative of 0 is 0, the first derivative of constant is 0. Here we have very sharp edge, so the first derivative tends to infinity. Now, in the discrete version, we don't have derivative anymore. We have first difference. We don't have integral. We have summation. Two system characteristics: impulse response and step response. If we apply delta at the input, the system output will be h of t, which is the impulse response. If we apply u of t, the output is g of t, which is the step response. When we know either impulse or step response, we know everything about the system. Now, the behavior of the system is clear for us, and if we apply another signal here, we can guess the output. For discrete system, we have also impulse and step response, but in sampled version. So for causal systems, our input response should be non-zero only for positive t values. If this is our impulse response, this is for causal system, because here we have 0. We have reaction at time greater than 0. For stable systems, we always want stable systems. For stability, the impulse response should tend to 0 when time tends to infinity. For stable systems, the impulse response approaches 0, always. for unstable system, when we apply a bounded input to the system, the output increases. Because delta and u of t are related by integral and derivative, for impulse and step response we have similar relations. If we differentiate the step response, we will get the impulse response, and back if we integrate the impulse response, we will get the step response. We don't need both of them, we need just one of them. For digital discrete time systems, instead of derivative, we have first difference. Instead of integration, we have cumulative sum. We accumulate. Now, if we have a discrete time signal x of k, and we have a signal x of n, we can express such signal if we multiply this signal by shifted Dirac delta. For now, this is not meaningful because we just express our signal by itself multiplied with shifted Dirac delta. For continuous time signal, the things are very similar. Instead of summation, we use integration. Our signal multiplied by shifted delta. These operations, this and this, are in fact convolutions with Dirac delta. Every convolution of a signal with Dirac delta gives us the same signal. Now, we have a LTI system which at which input we have this equality, and we apply system operator on both sides, left and right. If we apply this operator here, we will get output signal. But here, the principle of superposition is valid. So, the system output, when the input is Dirac delta, is the impulse response. When the Dirac delta is shifted in the input, the impulse response is also shifted, because we have time invariance. Now, finally, our output signal we have a system. We know its impulse response. If we apply an input signal x, the output signal y is equal to the impulse response convolved with the input signal. We have a convolution. And for continuous time signal, we have so-called convolution integral. So for LTI system, the output and input relations with when we know the impulse response are just a convolution in continuous and in digital flow. Because this here you can see the convolution process for continuous signal and for sampled or discrete signal. What is the convolution? We have to make the convolution between a rectangular pulse and an exponential. This is our input signal, this is the impulse response. This is our system. It has impulse response that is exponential. We apply rectangular pulse at the input. We want to know the output. Convolution is the following. This is our signal X. In the formula above, you can see the impulse response is not a function of t, but of t minus tau. This impulse response, we can flip it because we have here minus tau. This means flip in time. But now this variable t is the delay. We move this, multiply it by the signal, and we integrate the result. So the output of the convolution will be something like this, because the maximum will be somewhere here when we have significant overlap. This is here is analog convolution, here is in digital form. Here is much simple because we don't have to integrate, we have just to multiply and accumulate some. Some convolution properties. Commutativity, distributivity, shifting property, and convolution with Dirac delta. Convolution with Dirac delta gives the same thing. It just repeats the signal. Now, we want to make an analysis of our system in frequency domain. We define so-called frequency response. That is a function of frequency, complex function of frequency. It has absolute value and angle argument. By definition, this is the spectrum of the output over the spectrum of the input. And if you want to predict the output signal, and if we know the frequency response, it is very simple because we just have to multiply the input spectrum by the frequency response and we will get the spectrum of the input signal. As you can see, we don't have convolution anymore, we have multiplication. Convolution is in time domain, multiplication is in frequency domain. So because the impulse response h of t and frequency response h of j omega gives everything about the system. This gives everything about the system in time domain. This gives everything about the system in frequency domain, we expect a relation between them. And this relation is very obvious and simple. Continuous time Fourier transform. If we apply Fourier transform over the impulse response, we will get the frequency response. It is very easily proved because we know the spectrum of delta is 1, so the denominator here is 1, and finally h of j omega is Fourier transform of the impulse response. Now, from the frequency response, we can take the magnitude response and the phase response. Magnitude response shows us how the system attenuates or amplifies the amplitudes of the spectral components. Whereas the phase response gives information about how the system changes the initial phases of the harmonics of the present in the input signal. The amplitude spectrum is the output signal is the amplitude spectrum of the input signal times the magnitude response. The phase spectrum of the input signal is the phase spectrum of the input signal plus phase response of the system. Now, Laplace transform. Here we are going to talk about only for causal system. So the lower limit for this integral is 0. In fact, it could be minus infinity. It is very similar to the Fourier transform. Now we have a complex variable S, which has a real part and imaginary part. Our imaginary part is the frequency, and we have a real part. So if we take only the imaginary part, and if we substitute here, we will get exactly Fourier transform. So Laplace transform is generalization. In Fourier transform, we have just complex exponentials here, sine and cosine oscillations. Now we have sine and cosine oscillation, but with some damping factor. This is a damped sinusoid. So our kernel here is complex exponentials that decays. Why do we use Laplace transform? Because it is more informative than Fourier transform. It can tell us if the system is stable or not. The inverse Laplace transform, I gave it only for completeness. Nobody performs these awful mathematical operations because they are very, very hard. Some properties of Laplace transform are much similar to the Fourier transform: linearity, time shifting, scaling, derivative. This term is the initial conditions, integration. We divide by the operator S, and in derivative we multiply. Multiplication by cosine, modulation property, same as as in Fourier transform. Multiplication by sign, by completion exponential, and the product is equivalent to the convolution in Laplace domain. The convolution in time domain is equivalent to the multiplication in Laplace domain. That is one of the reasons that we want to use Laplace transform, because you just multiply instead of convolve. When we want to get back the signal in time domain from its Laplace domain, we usually consider this table. Here we have our signals in time domain and their Laplace transform. As you can see, for delta, the Laplace transform is 1. For step function, the Laplace transform is 1 over the Laplace operator, and so on. If we want to make an inverse Laplace transform to the time domain, we can express as a sum of some simple terms, which can be found here. If we can express our Laplace function as a sum of simple things, we can find them here, and we can find the original, because the Laplace transform is a linear transform. Transfer function. This is the ratio of the output signal to the input signal in Laplace domain. And if we know our transfer function, we can guess the output of the system if we know the input, but in the Laplace domain. We just multiply the Laplace transform of x by the transfer function, and we will get the output signal in Laplace domain. If we want this signal in time domain, we have to apply inverse Laplace transform on it. Of course, the impulse response and the transfer function are related to each other. If you perform forward Laplace transform on the impulse response, you will get the transfer function. Now, the transfer function can be expressed as a ratio of two polynomials, because it is a rational function, and we can express it in following form. We have z1, z2, and so on up to zn. We call these roots of the numerator zeros, and p1, p2, and so on are the roots of the denominator. We call them poles. Zeros make h of s to be 0, whereas a pole makes h of s to tend to infinity. The denominator here is the characteristic equation of our system. If we can find the roots here, we can find the poles, and we can make a pole zero plot that can tell us a lot of our system. The Laplace transform has region of convergence. This is the region when the Laplace transform is not infinity. Here is an example of a system with poles. Here is, and here, and here we have poles, and For a causal system, the region of conversion starts from the rightmost pole. If we have a system, this is our complex plane, sigma j omega. We have many poles. The region of convergence starts from the rightmost pole and it is here. For a stable system, ROC must include the j omega axis. So our poles have to be on the left side. When we have poles on the left side, we have a stable system. Here on the right side, we have unstable. You see, we have increasing, no stability. In fact, the poles can be complex or can be real. A real pole, like this, and complex poles, because the differential equation is with real coefficients, every complex pole is appears in pair with its complex conjugation. If the pole is real, it can be alone, but if it is a complex pole, it is always complex conjugated. Always. So if we have a real pole, if we apply for a real pole, this is our system. It has, let's say, step response. If we apply step function, if our system has real pole, the output will be something like this. It doesn't oscillate, but real pole. But if we apply such step function, we have complex pole. The reaction of system is that something like this. It starts to oscillate. If the system is stable, at time when time tends to infinity, the oscillation will be almost zero. But for unstable system, the amplitude of such oscillations increases with time. So as you can see, the pole zero plot is very interesting and can give us a lot of information about the system properties. Now, how can we guess the magnitude and phase response from the pole zero plot? We have here situation with two poles, and here we have situation with two zeros. And poles and zeros determine the system characteristic, but only the poles determine if the system will be stable or not. We have a pole and we have a point on the j omega axis, and we want to know the magnitude and phase response at this frequency. We can we can make a vector starting from the pole up to this point, the length of a vector and the angle. The angles of such vectors are summed. The lengths are multiplied. Multiplication by many lengths in our poles. For the zeros, the situation is the same, but we can sum all the angles determined by the poles and sum all the angles determined by the poles and by the zeros, and if we subtract them, we will get the phase response at that frequency. Similar thing for the magnitude response. All 0 points actually can be very useful to analyze the system. Simple systems, first order, RC, integrating circuit and differentiating circuit. When the system is with order of 1, we have the following differential equation. We have 6 dB per octave slope of the magnitude response. I will show this in the MATLAB. And for such systems, we have the time constant, which is R by C, and the cutoff frequency, because we have filters, low pass and high pass filter. The cutoff frequency for such filters is 1 over tau. If we have an integrating circuit, it can be described by the following equation, and we can find the transfer function very easily. We have tau, first derivative of the output plus output is equal to the input. Let's try to find the transfer function. We can apply Laplace transform on both sides. Tau is a constant. Laplace over y of t is y of s. But we have here first derivative. So in our table here, we can see that the first derivative we have to multiply by this. We have differentiation here. We have 0 initial condition, so we forget about this. Now we have tau s by y of s plus y of s equals to x of s. The transfer function is 1 over, I forget about this s, here, tau times s plus 1, I can divide by tau, and so 1 over tau s plus 1 over tau. Very easy way to find the transfer function. Just apply the Laplace on the differential equation, use this property. When we differentiate, we have to multiply by s in Laplace domain, and the things are relatively easy. This transform is very useful when we have to analyze transients in electrical circuits. We don't want to solve differential equation. We can transfer them with Laplace transform to algebraic equation, and we can analyze the circuit, and we can get back the voltage current in time domain just by applying the inverse Laplace transform using the table. So here is our transfer function. We just found it, and magnitude and phase response. We can found them very easy by substituting S with J omega. Input response, impulse response, and this impulse response is just by application of inverse Laplace transform over the h of S. For differentiating RC circuit, the things are very similar. Transfer function, magnitude and phase response, and step response. We can show this with short demo. Well, let's start with the integrating circuit. Magnitude and phase response in linear scale and in logarithmic scale. Here is the cutoff frequency at level minus 3 decibels. The cutoff frequency is 1000 radians per second, which is equal to 1/1000. For our simulation, tau is 1 millisecond. You can see the pole zero plot here. Our pole is here. The J omega axis is here. We have a real pole. So this system behaves like this. It doesn't oscillate at the end. The pole is here. The real part of the pole is 1000, which is exactly the cutoff frequency. And if we, this is the impulse response, as we expected, no oscillations, and step response also. If we apply input signal, when we apply a rectangular pulse train to the input, the output is the blue one. So the system behaves like integrator. If I change the transfer function, I can make the differentiation circuit. This is high pass filter, and here we have one pole and 1 0. If we apply rectangular pole strain to the input, the output is something like the first derivative of the input. The second order systems, for example, RLC circuit, series RLC, resistor, coil and capacitor, the following differential equation. You see the second derivative, so the second order. The slope is 12 decibels per octave. What is the slope? If we have low pass filter, this slope, if the filter is for first order, it is 6 dB per octave. Octave means doubling, increasing the frequency twice. If we have F1, 1 octave will be 2 times F1. The slope for first order filter is 6 dB, for second order is 12 dB. For second order system, we have natural frequency and we have damping factor, and our differential equation, we can rewrite this equation using the damping factor and the natural frequency. Magnitude slope is 12 dB, and here is the transfer function. Very easy to be found by applying Laplace on both sides. And we have a characteristic equation in the following form, which can tell us all about the system behavior. Three situations when the damping factor is greater than 1, this is called underdamped system. We have two poles, but they are real but different. So one pole is here and the second is here. This is underdamped system. Critically damped system is when we have two poles, but they overlap. And the third situation is overdamped system. Excuse me, here is mistake, overdamped system. When we have overdamped system, we have a pair of complex corrugated poles. The step response in such a situation oscillates. Here we don't have oscillation. When we have the critically damped system, the output still doesn't oscillate, but it reaches as fast as possible the steady state. we have two complex poles. This diagonals is the natural frequency of the system, and this projection here is the frequency of the oscillations in the output. If the pole is real, no oscillation, because the frequency will be zero projection. When we move the poles close to the j omega axis, the oscillations continue the system continues to oscillate for a longer time. When we move the poles to the left, the oscillations are attenuating very fast. We can see this behavior using MATLAB. We have values for L, C, and R. Magnitude and phase response in logarithmic form. Pole zero plot. As you can see, we have two poles, first and second. They are real. So no oscillations at the output. The step response is a periodic. When we choose a different value for R, we still have two poles, but their values, their real projections are the same. This is critically damped system. The impulse and step response decay very fast, but we don't have any oscillation here. If we choose another value for our resistor, let's say 10, magnitude response is not flat anymore, but we have now two complex poles. Here is the first, here is the second. And the system is oscillating when we apply an input signal. If I try to lower this value, let's say 1,
and more oscillations.
Yeah. What's going to happen if the poles are exactly on the j omega axis? Can you imagine? It will oscillate forever. This is a generator. By its feedback, the poles are always here. We can make this. I can try to set the value for the resistor to 0.
Or close to it.
Why not the computer simulations are very convenient. Wow. Two poles on the imaginary axis, and it oscillates forever. But can I make something weird?
Minus one.
In practice, it's not possible. Minus negative resistance means that we get energy.
From the
Not,
medium.
yes, from the environment. This system is not stable anymore. This will increase or will go up. Where are the poles? On right. No. Time to break.
Yeah.
Right.